Let's look at some special cases which may arise when you're trying to use mesh current method, which are not so straightforward to solve. As usual, we will consider an example circuit to see this. I'm going to use the two loop currents I1 and I2 as shown. Once we have the loop currents, the next step is to determine the branch currents. The branch currents induced by the loop currents are shown in the figure. Pause the video here to convince yourself that these are the correct branch currents. The next step is to write the KVL equations. In node voltage method, we write the KCL equations, and the equations are in terms of voltages. In mesh current method, we write KVL equations, and the equations are in terms of currents. I'm going to write a KVL equation on the left side loop corresponding to the loop current I1, starting and ending at that point, going in clockwise direction. First, I have a voltage increase of 20 volts. Then I have a voltage drop of 4 times I1 across the resistor. Note that at this point I cannot directly express the voltage drop across the current source in terms of other currents. I'm going to assume the voltage drop across the current source is V. Then I have a voltage drop of V plus another voltage drop of 1 times I1. That should be equal to 0. This is the KVL at loop corresponding to I1. Similarly, I can write a KVL at the loop corresponding to I2. I will stop and end at that point going clockwise. Going up, there is a voltage increase of V. Then there is a voltage drop of 9 times I2 plus there is a voltage increase of 90. Then there is a drop of 6 times I2. That should be equal to 0. Simplifying equation 1, I get this equation. Simplifying equation 2, I get this equation. I can add these two equations to eliminate V, and then I get 5 times I1 plus 15 times I2 will be equal to 110. Note that I have two variables and one equation. So at this point, I cannot uniquely solve for I1 and I2. If you go back to the circuit, however, you will notice that we have so far not used the fact that there is a current source of 6 amperes. Obviously, our solution cannot be independent of the fact that that current source has a value of 6 amps. That means we have to use that information somehow in our solution. Note that the branch current induced on the center bands by the loop currents will be I1 minus I2. And we know that that branch current should be 6 amps, which will give us our next equation, which will be I1 minus I2 should be equal to 6. Solving these two equations, I get I1 as 10 amps and I2 as 4 amps. If you noticed, the complication here was how to deal with the current source. A common mistake I observe when students write KVL equation, for example, in loop 1, is I see equations like this. Minus 20 when going up, plus 4 times I1 drop across the resistor 4 ohms. Then when they get to the current source, they don't know how to deal with it, so they just ignore it. And then there's a voltage drop of 1 times I1 equal to 0. And I very commonly see KVL equations like this, where students just ignore the current source and assume the voltage drop across that is 0 because they don't know how to deal with it. Don't make that mistake. Also, in order to deal with the current source, we had to introduce an extra variable V and then eliminate it. So instead of having two equations and two variables, for I1 and I2, we had 3 equations and 3 variables where the extra variable was V and we had to eliminate it first. Or alternatively, we could have directly solved the 3 equations and 3 variables. But there is a way where you can avoid the variable V altogether. Let's look at the same circuit again with loop currents I1 and I2. The problem previously was we were trying to write a KVL equation around that loop. And the problem was that we could not directly express the voltage drop across the current source in terms of the loop currents I1 and I2. So why don't we pick a loop which doesn't have a current source in order to write a KVL equation? For example, I could have picked a loop like this. So let's do it. We'll start and end at that point going clockwise. Going up, I have a voltage increase of 20 plus 4 times I1 plus 9 times I2, a voltage increase of 90 plus 6 times I2 plus 1 times I1 is equal to 0. Simplifying, I get this equation. Note that this equation here is exactly the same as this equation we obtained before after eliminating the voltage V or the variable V. However, since we chose to use a loop which did not have any current sources in them, we did not have to create a new variable to deal with the voltage drop across the current sources. So we got the equation directly in terms of I1 and I2 without having to deal with extra variables. And then obviously we also have the other equation where this branch current we know is 6 amps and the branch current induced by the loop currents would be I1 minus I2, which should be equal to 6 amps. And then we have the same two equations and two variables which we can solve. Let's look at the same circuit again. Instead, this time, I have the loop currents as shown. I1 is the same as before, but I2 loop current is the loop current going through the outer loop. So what is the advantage of this? If you notice, the branch current induced in the center branch by the loop currents will be equal to I1. And we know that branch current should be equal to 6 amps. So I immediately know that I1 is 6 amps. So now I'm going to use the knowledge that I1 is 6 amps and write the KVL equation around the outer loop. As usual, I will start at the left corner and then go in clockwise direction. First, I have a voltage increase of minus 20. The branch currents from left to right through the 4 ohm resistor is I1 plus I2. So the voltage drop would be 4 times 6 plus I2. Branch current through 9 ohm is I2. So the voltage drop is 9 times I2. Then I have a voltage increase of 90 volts. Voltage drop across the 6 ohm is 6 times I2. The branch current through the 1 ohm resistor is I1 plus I2. So the voltage drop is 1 times 6 plus I2, that should be equal to 0. Simplifying, I get this equation, and I2 should be equal to 4 amps. So by choosing the loop currents appropriately, I reduce the number of equations I need to solve this circuit from 2 to 1. So here are some simple rules you can follow while using mesh current method. First, when you have current sources, make sure that you have a single loop current going through that branch. Why? So that you can immediately figure out what that loop current is. 2. When writing KVL equations, avoid loops with current sources. Why? So that you don't have to use that extra voltage variable. The use of a loop like this instead of traditional loops like this is called the supermesh method in your textbook. And again, as you might agree with me, there is no need for special names in this case. Just follow these simple rules.